Hello everyone, welcome to Chip Confessions. In our new design verification course for batch 1, this is the second video in this series. Let us see what we are all going to learn in this session. In this session, we are learning about what is a design, what is verification means, what is chip mean, and what are all the types of the chip, what is ASIC design flow, and what is ASIC verification flow. If you can think why all these things needed, we could have directly headed with digital electronics and Verilog. But my intention is, if you are learning design verification, you must know what does design mean, and what does verification mean, and what is a chip. And as we are concentrating on ASIC here, we should know what is the design flow for ASIC and what is the verification flow for ASIC. Let us see one by one in rest of the slides. What is a design? Whenever we think of design, what comes to our mind is some pattern or some painting or anything on any kind of platform which is eye-catchy. So, but what does it mean in terms of VLSI? If we see that, we can say a design is nothing but a description of some digital circuit or any digital system. For example, if I take adder, then a design is nothing but the description of that adder. Means design is giving us what does that adder do. So collecting everything, if we say what is a design is nothing but description of a digital circuit or a system. And at the very beginning level, this design will not be in physical form. It will be in the form of a code. So we need some language to write that code to represent this design. For that, we will use some language, and that language is called as HDL or hardware description language. So a hardware description language is a type of language we use to write the code which describes some design which is nothing but a digital circuit or a digital system. Putting it all together, what is a design means, we can say in terms of VLSI, a design refers to the hardware description of a digital circuit or a system which is typically written in any hardware description language or HDL such as Verilog or VHDL. This design will describe the functionality that a digital circuit does. For example, as I said, adder, subtractor, or a comparator, or a D flip-flop, all these things are example for this design. Now let us see what is verification. If we see what is verification, in general terms, verification is nothing but we are checking something. Very basic example, if I take, whenever we prepare some food, what we will do, we just taste, just to check whether it is tasting proper or not. If there is some issues, like if salt is less, or if it is more spicy or less spicy or more salt, then we will make some corrective actions so that that food will taste in a better way. Same thing if we apply for VLSI. Here verification means we are checking that the design is working correctly or not. We will be having some kind of description or functionality list which is called as specification. Means, as I said, if we just take an example of an adder, it should add two numbers. For simple task we shall take, it should add two numbers, say A and B, and whenever we are adding A and B, the sum should be correct. and we will be verifying or checking whether that sum is correct or not with the help of verification. So, verification can be defined as a process in which we are checking a hardware design working correctly or not. If it is working correctly, then it can be taken further for fabrication process. If it is not working correctly, then we will see how it can be fixed and how it can be made to work in a correct way. So there will be something which is called as a specification, and based on that the design should work, and that design is working or not meeting that specifications will be checked or tested with the help of this verification action. And that design which is being tested will be called as design under test or DUT. You can ask, anyhow we have written the design and it will be complying with the specification only, then why we need this verification? If you have that doubt, then we can say verification is needed just to ensure that design is working correctly before it is physically manufactured. Means at a coding level itself, we have to check whether that design is working properly according to the specification or not, because once it goes for physical fabrication, we cannot make any further changes in that. So any addition or any deletion or any update, whatever we have to do, or any corrections we have to make to the design, everything will be done at the coding level itself, so that there will be no loss or no further waste of cost or waste of money on that. That's why verification plays a very important role while ensuring the chip or the design of the chip working according to the specification or not before it is physically manufactured. Let us see then. Till now we were saying like chip design or whether the chip is manufactured or not, like that we were using the term called chip. Let us see what does this chip mean. What is a chip? A chip is nothing but, we can say, a small piece of silicon. You know what is silicon? A silicon is a element, and with using that we are manufacturing the chip, like using that silicon dioxide and all we studied during our college days, or even before that in our high schools also. I will not get into those things now. If at all I say what is chip, then we can say a chip is nothing but a piece of silicon or a small piece of silicon which contains millions or even billions of transistors, and it also houses some blocks or elements such as memory block or a group of flip-flops or any other blocks. Means basically a chip is nothing but a small piece of silicon which contains millions or billions of transistors. Let us see what are the types of the chip now. We saw the description of a chip. Now we shall see what are all the types of the chip. What are all the types? A chip can also be called as IC or a microchip or even a silicon chip. If we see the types of the chip, we have first like means this is a very vague, which we don't have any basic standard for this types actually, like not we have just describing the general types of chips here. On means we are not like based on this or that we are like describing this or not, nothing like that. Just like that we are just generally in a way we are just telling the types of the chips. So first is the CPU. CPU is nothing but the central processing unit. which is used for general computing, and it is mainly used in computers, desktops, laptops, phones. Means it will be like for general computation. It houses your ALU, it houses your memories. It likes that. It's like that. And you know all CPU means in your desktop and all you will be seeing these things. That is nothing but your CPU, which is generally seen everywhere. Next is microprocessor or microcontroller. This is used for like simple controlling task. For example, say washing machine or your AC, like that. It is mainly used in home appliances where for smaller scale or only like repeated controlled kind of task we use this microprocessor or microcontroller. Then third type is memory chip. Memory chip is nothing but like RAM, we have random access memory or read only memory or a flash memory or a cache memory. We have these kind of memories, and the main job is to obviously store the data. And example we use in phones, we have USB, we have, and we have even SD cards also, like that. Then we have ASIC, which is nothing but application specific integrated circuit. This is this is on which we are going to learn in our course. And this is like task specific. If we are doing for some, for example, say we are doing for FFT, or we are doing for DFT, or we are doing for image processing, or we are doing for some camera IP, then this is like this ASIC will be task specific, means whichever you tell to do or which specification for which you build this ASIC, it will work for that only and nothing else. For example, if you say Wi-Fi, and this will work for Wi-Fi only and nothing else, it is like that. Then comes the FPGA, and FPGA is like general thing, means this is a reprogrammable chip. What we will do here, whenever we are going for ASIC, instead of like ASIC means it will cost more and it will take much of the time, and directly whenever you are doing a new design, you can't directly jump into something which is new, and you can't do trial and error here. So what we will do, we just deploy that prototype or deploy that new design on FPGA, and we will check how it is working. Then if it is working like say 70 to 80%, if we are sure, then we will continue with the ASIC, like that it is. So mainly FPGA is used for prototyping and testing the new designs. Then we are going for GPU. Then GPU is nothing but for parallel processing and graphic processing. For those things we are using GPUs, and this is especially used for like AI computation, or you have quantum computation, or you have your gaming laptops and all, where you will be like graphic processing is very much important. For that applications we are using GPUs. Then we have analog ICs. Analog, as the name itself suggests, it will deal with the real world signals like analog signals. Example say audio signal, video signal, and we have temperature, pressure, voltage, like this, sensor signals. This analog ICs will be dealing with these kind of things. Then we have PMICs, which is called as power management IC. This will be used to manage the power flow. For example, UPS we have, in that we will be having the batteries. In mobile we will be having the batteries. Means wherever this batteries and voltage control will come, there we can deploy this PMICs or power management ICs, which are mainly concerned with management of this power flow and voltage flow and all. This is the types of the chip, means this is a general type of the chip. Then next we are going towards ASIC design flow. This is very much important, and this will be even asked in the interviews also. Let us see what are all the stages or steps involved in this ASIC design flow. Initially this will be the specifications, means whenever we are going for a design, we will start with the specification. Then what is this specification? This specification, as I said in the description of the design, this will tell what a chip should do. This is the functionality of the chip. means specification is nothing but it describes the functionality of the chip, means the target what the chip has to do. And we will be having a document called as specification document. This we have to do in this is feature extraction. We will do what are all the features this specification will have. That feature we will list down based on this specification. That feature listing down is nothing but the listing down of the functionality. Later on, what we will see is the RTL design, means either we will use Verilog or we will use VHDL, and using that we will be writing the design. And RTL is nothing but register transfer level. So we will be writing a very basic code in this using Verilog based on, means which are all the methods, like we have data flow, we have behavioral model, we have like that. By using the models we will just write the code either in Verilog or VHDL, which is hardware description languages. And this will describe the functionality of the chip at the code level, means this will be at the software level. Till now we will be dealing at the software level itself. And later on it is the functional verification, means whatever we have written at a coding level using this hardware description language, that will be verified at a functional level. Here in this functional level, functional verification level, we will see whether that coding or the code we wrote is complying with the specification or the feature we listed. If it is working fine, then we can go further, or if it is not working fine, or if we see any bugs or issues, then we will go back and we will correct either the code, or if we have any fixes at the test bench, that we will do. How this functional verification is done means with the help of test benches, with the help of assertions and coverage. And coverage we will see like code coverage and functional coverage, both we will use, and we will do the functional verification. And this functional verification, say it will take up like 60 to 70% of the whole design cycle, because that verification has to be done exhaustively so that we are not going to miss even a single feature of that specification of the design. Later on, after this functional verification, what we are seeing is the synthesis. In this synthesis, once the verification is done and the design is freezed, what we are doing is we are converting the design into a gate level netlist, and everything will be represented in terms of logic gates. And we will be like using specific technology, and some libraries will be there like 7nm library or 28nm library, like this. Using these kind of libraries, means using these kind of specific technological libraries, we will be converting the code level to the gate level netlist, and this will be mapped to actual hardware cells. And till now we are still at the software level only, we have not entered into physical level. Later on we will do timing analysis. Once that logic gates everything are done, then we have to check for the timing, whether the design is meeting the timing requirements such as speed or clock delays, whether everything is fine or not. That we will be checking at STA, because we have to ensure the data is moving correctly across the chip. Means we will be having the flip-flops, we will be having the logic. Flip-flops are nothing but basically the logic gates. We will be having the combinational blocks, we will be having the sequential blocks. There we have to see whether that delay is properly, delay will be there, but the delay should not exceed the described delay. That will be checked at STA level. Later on, once this timing analysis is checked, what we are going is for floor planning. Here what will happen is we will see where that, as I said before, we will be having blocks like combinational blocks, sequential blocks, like we will be having memory blocks, IO blocks, or any logical computational blocks. Those blocks we will be having, and in floor planning we will see where those blocks could go and sit. That we will check at the floor planning level. And then we will go for placement. What we will do in placement, once planning is done, what we will do is we will place those blocks. On that we will be defining a layout of the chip, and after defining a layout of the chip, layout is nothing but like I can say the area of the chip, and within that area, as we have planned, we can just roughly compare it with where if you are building a house, where should kitchen go, where should room should be, where your hall should be, like that, where your puja room should be, like how we plan. That is nothing but your floor planning. You are planning here it should be there, here it should be there, like that. And placement is nothing but you are actually placing it in a planning, and you are seeing how it looks. That is what placement does. Then is we are going to CTS. CTS is nothing but clock tree synthesis. Once that placement and all is done, you should see whether that placement is proper or not, because we will be having a clock, and that clock, if we have flip-flops or if we have flip-flops like sequential blocks we will be having, that clock should reach to all the flip-flops simultaneously. That is what your synchronous design is. That will be checked in CTS. For example, if I say you have built a kitchen and your dining hall should be adjacent to the kitchen. You are building a kitchen at one corner, and if you are placing your dining hall outside somewhere near the gate, it's funny, but still, how if you are keeping your dining hall outside the gate or outside your home, it's like it doesn't mean anything. So it should be your dining hall should be adjacent to your kitchen. That is what your CTS do. After your placement, it will check how the clock will go, or how the clock can reach everywhere, and what time. Means here also, like, we will be ensuring the clock signal is reaching all the flip-flops at the right time. Delay will be there everywhere. We can't say zero delay, because zero delay is such an ideal condition, it can never exist. So what we can see is at the right time whether the clock is reaching or not. That we will see in clock tree synthesis. Then the next step is nothing but your routing. What this routing will do, it will connect. We have already planned, we have already placed, we have even checked for the clock whether reaching or not properly. Then we are connecting each and every block. We will place these cells and we will connect them, and we will ensure that signal is traveling between these components in a right way. That we will check at the routing level. Then we will see physical verification, like why this physical verification is needed. Till now we have not entered into physical verification. Means it's not like we will be having a chip in our hand and we are seeing everything. No, we are still at a software level only. What we are checking here is we are checking whether the design is complying with the layout. Like we will be having two things here. One is the DRC and LVS. What is DRC? DRC is nothing but the design rule check. We have done the layout, we have placed everything, we have everything ready. What we have to see whether after this placement and routing it is complying or following the manufacturing rules provided by the foundry. Foundry is where your chip is getting fabricated into a physical entity which you can touch by your hand. So this DRC or design rule check, it will verify or checks whether the layout whatever we have put, it will follow the manufacturing rules provided by those foundries or the fabricational units. For example, you know, TSMC, or we have even Intel also, those things. The rules whether it is followed or not will be checked by DRC. LVS is nothing but layout versus schematic. Means whatever the layout you have done, whether that is complying with the physical design, that is the schematic. Means it compares the layout with the physical design and ensure they are electrically identical. means the schematic and the physical design are compared, and we should be ensured that correct number of transistors are placed, correct number of gates are there, or the proper connections are there between them, whether they have proper matching names, proper matching pins. That and all will be checked in layout versus schematic, that is LVA stage. Whether means this is like ensuring the layout is matching the exact logical design and it is complying with the manufacturing rules. Then what we see is the sign off. Sign off where means after doing everything, whether the timing means we will again be checking for timing rules, means it is like final checks will be done here, power analysis will be done, timing checks will be done, and whether the signal integrity is happening or not, those things will be checked at this sign off stage. After passing this sign off stage, now the chip is ready for fabrication. Sorry, the design is ready for fabrication. So we can go for the fabrication which gives us tangible, or the chip we can touch by our hand. So next is the tape out. Tape out is your end of the design where the final design is sent to the foundry for fabrication, where we can get the chip. And this is the last stage before the chip is physically built. If you are going for sign off, it is like you are already at the end, and tape out confirms that officially your design is ended, means the software level is ended and we can go for fabrication. This is what our ASIC design flow is. I hope you understood all these things. Later, or the next is our ASIC verification flow. Let us see one by one what is ASIC verification flow containing. As I said, verification is the part of ASIC design flow which makes up to 60 to 70%, and roughly we can say it is 70% of the design time will be taken up by the verification itself. This shows how important this verification is. Means whatever the bugs or whatever the issues or whatever the mismatches we find, everything 90% we should find at this level only, and we should fix those things. Because at this level, if you are catching the bugs and if you are fixing it, this will not cost you much. But once the chip is fabricated and you have chip in your hand, say you have a phone and inside that you have put a chip, and that chip, if you do switch off, it is switching on, if you do switch on, it is switching off. This is insane, but still this is a problem only. So like this it should not happen. So verification is a very critical stage in your ASIC design flow cycle. Let us see what are all the steps involved in this verification flow. Let us see one by one. First is the requirement analysis. What is this requirement analysis? Requirement analysis is nothing but extracting or understanding the chip specification. As I said, adder, we have two numbers and we are adding it. We should see like how many bits that number should have and how it should add, whether it is generating carry, where it is storing the carry, whether it has any other thing, as does it have clock, does it have reset, what are all the signals it is involving, or any extra things we need to check, or any extra specifications it is having. Everything will be done at the requirement analysis stage. This is where we are understanding the chip's specifications and we are defining what and all needs to be verified. And based on this, we are preparing a verification plan. And this verification plan will include the list of the features, test scenarios and metrics. Metrics are nothing but the specifications that need to be tested. And this is this will be containing the detailed plan of everything. This will contain like test plan also, what are all the test or what are all the features we are targeting, and whether we are doing a directed test, random test or a corner test, whatever the things test we are doing, this verification plan will hold all those things. And then the test bench architecture, and how much of time we need to do, what are all the resources we need, everything will be involved in this verification plan. And then we are moving towards the test bench development. You extracted the features, you listed the specifications, you listed the test cases. Then you have to develop the skeleton of your test bench. That is, we are doing test bench development. We are developing an environment here. And what are all the things this test bench should have? Those are all the components we are creating here. And we will be having like monitors, scoreboards, and we have like checkers and assertions, whatever it is needed for the test bench, that and all will be developing here in this test bench development stage. Then we will be having the simulation stage. Simulation is where whatever the test bench architecture you created, you are executing that. We will run this RTL design, means we will connect RTL design with our test bench, and we will run that design code inside our test bench. And we will be checking whether that output of the design is matching with the expected behavior. And we will find if any discrepancies are there, any mismatches are there, or any issues are there, any bugs are there, that we will find out here, and we will catch those bugs and we will try to fix them. Then is the functional coverage. This functional coverage is nothing but this will measure like how much specifications we have already tested. Like we will be having say some hundreds of specifications listed. Out of 100 specifications, how much we have tested. If we have say tested 50, then we can say 50% of verification is done. If we say we have tested 70 out of 100, we can say 70% of verification is done. This functional coverage gives us how much verification is done. And it will also helps us to identify whether are we missing, if we are missing any features, or any corner cases to be included, or any additional test cases are needed. Everything will be guided by this functional coverage. And this functional coverage is completely like user dependent. We are only creating we are only listing out the specifications, we are only creating the test cases to test those specifications. It is like everything will be in the user's hand or the verification engineer's hand. For say we have 5 features to be tested, and if you list out only 4 features, though the functional coverage says you have been covered the design by 100%, but as you have missed a feature, you will be missing that 20%, you will be only 80% covered. But in the document it will be like 100%, but in the real time or in the reality it will be only 80%. So this functional coverage is completely in the verification engineer's hand. So we need to be very careful while listing out the specifications so that we should not miss any of the features, as this will give us the track of verification where we are standing and how far we have to go. This will be given by the functional coverage. Then we will go for formal verification, means this is optional actually. It is not like compulsorily we have to do, but this is like optional. Sometimes we will be like if we have more number of like anything that has to be tested, such as like if we have mathematical blocks or computational blocks, at that time we go for formal verification to check, means it is completely based on the properties. We are writing the properties, we are assuming some properties, and we are just checking those properties that should be held true for all the time. Means whenever we are checking say corner cases, at that time also we can use this formal verification. Like If it is very difficult to reach out with the help of functional coverage, then we can employ formal verification there. Then is debug and fixing bugs. Means it is like a cycle. Verification, we can't say verification is done 100% done and we are done with the verification. No, we can never say like that, because that addition RTL changes will be happening and your verification cycle will also, sometimes you need some more test cases, sometimes in a single test case we can you can test more features. Like this will be keep on happening, and it will be exhausting also. Like you will feel like when this will get over, when I am going to finish this, like that sometimes you may feel. Like we will be testing, we will be debugging, we will be fixing the bugs, or we will be correcting the mismatches, that will keep on happening. And then it is like regression testing. Regression testing cannot happen at the end. We can employ, like whenever we feel like we have finished some 20% or 30%, since from then only we can include regression testing. It is like one after the other the testers will be the test will be running, and then we will see any discrepancies are there. And some more situations are like some minor changes will be done in the code, and then we have to check, means there we can employ this regression testing. There means we will run, as I said, all the tests repeatedly whenever there is a change in the RTL code. It will ensure, means after fixing the code, that code is not breaking or it is not breaching the specifications. And then next is the sign off. Once we are done with the regression testing, and once we feel like the functional coverage is like near to 100% or 100%, then we can say that we can do verification sign off. And sign off tells we have achieved the required coverage goals, means we have thoroughly tested all the specifications, and then no bugs will be there, like minor bugs will be there. We can't say like 1000% we have done everything and I'm damn sure it will never create any issues. No, we can never say like that. What it says is, the sign off says is, no critical bugs remain. Like no bugs will be like it will break the system down or it will affect the system. Such kind of bugs will not be there. That is what this verification sign off will tell you. And then our design is ready to go for synthesis level. This is what this sign off tells. One thing is, we have already achieved the desired coverage, that is the specifications whichever listed, everything have been tested and they are thoroughly, and our design is thoroughly working fine. And then we do not have any major or critical bugs that can affect the system performance. And then our design is ready to go for further stages such as synthesis and physical verification. That is what our verification sign off will tell. This is what our ASIC verification flow is. So in this session it was so exhaustive, yes, but we got to know what is a design, what is a verification mean, what is a chip, and what are the types of the chips, and how we divided those things, like general division we just saw, and then ASIC design flow and ASIC verification flow. I hope you got some knowledge from this session. From the next session we shall start with our actual syllabus. Thank you so much. Keep coding, keep learning. Stay tuned for our next session. Please like, share this video and subscribe to Chip Confessions so that you will not miss any updates. Thank you so much. Thank you, and have a great day.